All right, it's 5:30. Let's go and get started. All right, good evening, everyone. How's everyone doing today? Good, good. All right, it's the end of week 11. So Thanksgiving's in coming up soon. I know on the one hand, I think everyone's dreading Thanksgiving because that's when the midterm's going to be. But on the other hand, having that week off will be nice too. So that's definitely something to look forward to. Okay, so everyone's midterm projects are in. So I did see that pretty much everyone's turned it in on Canvas. I haven't started looking at them yet. My plan is to start looking at them tomorrow afternoon. It's probably going to take me a couple of days to grade them just because there's a lot of you and it's a lot of reading for the reports. But my plan is to finish all the grading before next Tuesday. In fact, I spent most of this week catching up on grading for all my classes, and so finally caught up with all the grading. So I should have time to grade the project. Look forward to have that being done by Tuesday. Okay. Okay, and so with that said, the next thing that we have coming up is the midterm exam, and so that's going to be the Thursday before Thanksgiving. And so the midterm exam is going to be basically all based on all the direct stiffness stuff. So the homework set that is out there right now, that is your #1 practice for the midterm exam. Okay, so definitely take a look at that. The homework problems, they do take a while just because there's a lot of writing to do, a lot of things you have to punch into a calculator. So make sure that you get on that. Okay. Okay. So the plan for today is I just have one more example with distributed loading, and so we're going to work on that for maybe the first 30 minutes class, and then we're going to move on to the next topic. And so from here on out, we've essentially finished the core of the course, and so we've gone over kind of the basics and more of ANSYS. We've gone over all the direct stiffness stuff, and so usually at this point, my plan for the finite element course is to go over kind of more niche features in ANSYS. So maybe not features you would use in every single simulation, but it can still be useful in certain cases. And so the first one we're going to do is actually unsteady simulations or dynamic simulations. And so that'll be the subject of activity 5. So we will do activity 5 before the Thanksgiving break. And so I'm planning for activity 5 to be next Thursday. It's not going to be due until after Thanksgiving though, because I want you guys to focus on studying for the exam, but just timing wise, it just kind of works out best to do it before Thanksgiving. So we're going to do the activity next Thursday, but it's not going to be due for like a month. And so just so you guys have time for the midterm exam, I'm not going to have it due over Thanksgiving. That's ridiculous. And so it'll be due kind of right when we come back from Thanksgiving. Okay. And then after Thanksgiving, up until the end of the semester, you guys are going to be pretty much just focused on just the final project from there. Okay, so that's basically the plan moving forward. So a lot of big events, and so the midterm exam, final project, and so it's going to be a lot of stuff. It's going to come very quickly, so you want to make sure you're kind of on top of all this stuff. Okay. All right. Any questions on anything before we get started for today? Yes.
Would you say like, as far as like studying the exam goes, would you focus more on like the examples we get in class or like the actual study?
So it's going to be a balance of both. So so my exams usually have a good mix of conceptual problems, and so conceptual problems usually make up about 40% of the points. And so you should definitely be reading the lecture notes, going over the lectures for those. And then 60% of the points are going to be from like actually doing problems. So like the examples and like the homework problems. So yeah, that's what I recommend.
Are we allowed like a cheat sheet?
Yes. Yeah. So for my exams, I allow you guys to have a cheat sheet on the exam. So that's 1 8.5 by 11 sheet. You can write on both sides. You can write it or type it. Yeah, we'll talk more about this the logistics of the exam next week. But yeah, I am planning to allow a cheat sheet. All right. Any other questions before we get started for today? Okay. So actually, before we get started, I did want to show you guys something. It has absolutely nothing to do with your class. It's just kind of fun. So I do want to let you guys know that I am very self-aware that if you ever grow up and want to teach engineering, you have to be a pretty big nerd to want to do that. But I want to show you that this is not like a recent thing. I've kind of always been like this. And so I've been going through a lot of old pictures recently, just because I'm planning a wedding for the end of this semester, and my mom sent me this picture from 2011. And so in 2011, my sister was graduating high school, and so that's kind of like a pretty big life accomplishment for her. But you should kind of see what I'm doing, and at her graduation. Okay, so that's me 12 years ago. So this is at my sister's graduation. There's my mom over there, like actually, being supportive and talking to my aunt. But look what I'm doing. You guys might know that textbook. That's the freaking fluid mechanics textbook. So look at me reading fluid mechanics at my sister's graduation. And so my mom sent this to me, and she's like, "I can't believe how much of a nerd you were back then." I'm like, "Mom, I'm still a nerd. I teach engineering for a living." So that's I've always been like this. This is 12 years ago to today. I haven't changed that at all. It's also funny that we still use the same fluid mechanics textbook today as we did 12 years ago. So I still have that textbook in my office too. I actually totally forgot about that until my mom showed it to me. Showed it to me recently. Okay. Anyway, all right. So let's get back to it. So what we were covering on Tuesday before we left off was talking about this idea of distributed loading, right? So I'm gonna kind of scroll up to a good picture. Okay. Okay. So distributed loading is something that we've been using in ANSYS a lot, right? And in fact, that's kind of the preferred way that I've told you to apply loads is to distribute it over a surface or distribute it over an edge. You want to avoid applying loads at a point, okay? But kind of the conundrum that we have here is that in order to actually apply loads into your finite element system, into your global linear system, that giant matrix thing, we actually do have to compute the loads at a point, because that's kind of exactly how it's entered into the matrix. Okay, and so to actually use a distributed loading in a finite element situation, we have to kind of go through this conversion process to convert it into a nodal one, right? So we have to kind of go from the image on the left to the image on the right. Okay. And so to do that, we're using this concept of work equivalence. And so what we're saying is that the work done by the distributed load should be equivalent to the work done by the nodal loads. Okay. And we kind of have this equality relationship here, where on the left-hand side, we have this integral equation where we integrate the distributed load together with the nodal, together with the shape functions for the element. Okay. And that's going to be equal to the nodal loads on the right. Okay. And so the example that we're going to do today is I'm going to show you how to evaluate that integral on the left for a fairly simple distributed loading. Okay. Okay. So let's kind of come back down here. Okay, so let's look at the following example. Okay? And so we're going to do this within the context. And so, of course, we're solving these equations within the context of beam equations, but the same principle will apply no matter what type of element that you use. Okay. And so, of course, the exact equations and the exact formulations that are used in ANSYS are going to be different, because they use, tetrahedrons, hexahedrons, things like that. But the kind of the general concept and the idea is like that. Okay. Okay, so let's draw our beam here. Okay. And so on one side of the beam, we're going to have a pin support. And on the right side of the beam, we have a roller support. Okay. So this beam is basically simply supported. Okay. So there's just enough constraints to prevent any kind of rigid body motion. Okay. And on top, we're going to have a distributed loading, but it's going to be a ring. So we're going to start with 0 on the left-hand side, and it's going to ramp up just like that. Okay. So it's a load that's going to increase as the value of x increases as well. So actually, let me draw this as well. So we're going to say the x direction is given from going from left to right, and we're going to assume that the origin of the system is at the left pin. Okay. So right here is x is equal to 0. Okay. Okay. And so we can write a functional form for this load, and so that's going to be our w of x function. Okay. Remember, for these distributed load problems and for FEA problems in general, the load is going to be given to you. Okay, it's not something you have to guess. Okay, and so because it's a linear ramp, you can see that our load function is a linear function in x, and so we say w of x is equal to 5,000 x, and the units for this is going to be newtons per meter. Okay. All right, and then we're going to say that the total length of this beam is going to be 1 meter. Okay. Okay, so there's no finite element problem that we're going to solve here, and so all we're going to do is we're going to compute the nodal loads. Okay. And so in other words, if we call the two ends of this beam, so we'll call the left end node 1, we'll call the right end node 2. Okay. What we want to compute is F1y, M1, F2y, and M2. Okay. So 4 things we want to compute from this, and it's all going to come from that work equivalence formula. Okay. Okay. Okay, so let's go ahead and set up that formula. And so our work equivalence formula is the following. And so we're going to integrate from 0 to L of W of x times dy of x dx. And that's equal to F1y d1y plus M1 theta 1 plus F2y d2y plus M2 theta 2. Okay. Okay. So let's go ahead and plug in our expression for W of x. And actually, we're going to ignore, well, not ignore, but it's just, the right hand side of this equation is not going to change. And so we're just going to work on just the left hand side. Okay. And then we'll bring back the right hand side at the end once we're done. Okay. Okay. So we have integral. Let's go ahead and plug in our value for L. So we know in this case L is just 1. So we're going to integrate from 0 to 1. W of x is 5,000x as given to us in the problem. Okay. Then we're going to plug in our function for dy of x. Okay. So this is what we covered at the end of class last time, right? So this dy of x is essentially going to be our shape function for our beam element. Okay. And so this is where things are going to differ. And so when you're doing this kind of calculation, a distributed load calculation for a different type of element, the shape function is going to be different, kind of as we discussed in previous classes. Okay. But for now, we're going to use the cubic function that we know for beams. Okay. And it's quite a doozy. Okay, so we plug in for dy of x here, we get 2 over L cubed d1y minus d2y. Okay. Plus 1 over L squared theta 1 plus theta 2. Okay. All this is multiplied by x cubed. Okay. Okay, then we have the x squared term, and so this is a minus 3 over L squared times d1y minus d2y minus 1 over 2L, or excuse me, 1 over L, 2 theta 1 plus theta 2. This is multiplied by x squared. Okay. Plus theta 1x plus d1y, okay, close bracket, dx. Okay. Of course, we know that L is equal to 1 here, so we can plug that in a second. But I wanted to start with kind of the raw expression for d1y, for dy of x. Okay. it looks really scary. And in some ways it kind of is, but if you kind of just focus on just the x terms, because remember we're integrating this in x, you're going to see that it actually simplifies quite a bit. It's not as scary. It's just a lot of symbols to kind of keep track of. Okay. All right. So before we integrate this, let's simplify it a little bit, just so that it's a little bit less intimidating. And so first thing I'm going to do is I notice that factor of 5,000 is just a constant multiplier, and so I'm going to pull that out of the integral. Okay. Next thing I'm going to do is I'm going to take x and I'm going to multiply x throughout this entire equation. Okay. And then I'm going to plug in a 1 for L. Okay. So let's go ahead and simplify. Okay. Okay. So first thing, let's pull 5,000 out. And so that 5,000 is going to be outside the integral. And so we have 5,000 times integral from 0 to 1 multiplied by. I'm going to plug in 1 for L. So that actually simplifies things quite a bit. So we have the 2 times d1y minus d2y plus theta 1 plus theta 2. Okay. Because 1 over L squared, when L is equal to 1 is just 1. Okay. So 1 over 1 squared. This whole thing is multiplied by x to the 4th power, okay? And so we increase the power of x because we have that x that comes in from the w of x, okay? So that increases all the powers of x all throughout. Then we have the next term in parentheses, and so we have a minus 3 over L squared. And so it's going to be a minus 3 times d1y minus d2y minus 1 over L, where L is equal to 1. This is going to be minus 1 times 2 theta 1 plus theta 2. Okay. That whole quantity is multiplied by x cubed. Okay. Again, we're increasing the power of x by 1 because we had an x that comes in from the w of x. Okay. Okay. And our last two terms are pretty simple here. So we have a theta 1 x squared plus d1y x. Okay. And we're still integrating with respect to dx. Okay. So again, we have a lot of terms here, but remember, there's only a few x terms, and everything else that's not x, we're going to assume that it's constant. Okay. And so when we perform the integrals here, we have basically four terms that we need to integrate, and we're just going to integrate them kind of one by one. Okay. Okay. So the next step here is to integrate. Okay. So I'm going to leave that 5,000 out there. So the 5,000 is going to be kind of just a constant multiplier throughout this entire thing. Okay. I use square brackets here because we're going to enclose everything in that. Okay. So everything that's multiplied in front of the x's, I'm just going to bring down. So we have a 2 d1y minus d2y plus theta 1 plus theta 2. Okay. We have integral of x to the 4th, and so that's going to be x to the 5th divided by 5 plus minus 3 d1y minus d2y minus 2 theta 1 plus theta 2. X to the 4th divided by 4. Then we have the integral of theta 1 x squared, and so that's going to be theta 1 x cubed divided by 3 plus d1y times x squared divided by 2. And we're going to evaluate each of those x terms between 0 and 1. So it ended up that we just had a bunch of kind of simple polynomial integrals to evaluate. Okay. So the next step here is we're going to evaluate these bounds, but with the bounds being 0 and 1, this ends up being very simple. Okay. And so I'm going to evaluate each of these individually, just because they're all kind of added to each other. Okay. And so remember, when we apply bounds for an integration, we only apply those for the, for the independent variable, which is x in this case. Okay. Okay. And so when we evaluate it for x to the fifth divided by 5, this is going to be 1/5 times 1 raised to the 5th power minus 0 raised to the 5th power. Okay. You can have 0 raised to the quadrillion power. It's still going to be 0, right? And so the second term is going to be 0. And you can have 1 raised to the quadrillion power as well. And that's all, it's still going to be 1. Okay. And that theme is going to persist through every term here. So the x fourth divided by 4, we're going to have a 1/4 times 1 to the 4th power minus 0 to the 4th power. Okay. X cubed over 3 is going to be a 1/3 times 1 cubed minus 0 cubed. Okay. And then this x squared over 2 is a 1/2 times 1 squared minus 0 squared. Okay. Basically, all of those x terms are going to be 1. And so basically the only artifact that we get from the integrating is just the fractional terms out in front. So we have a 1/5, a 1/4, a 1/3, and a 1/2. Okay. Okay. All right, so now that we have everything in this form, let's go ahead and simplify. Okay. And by simplify, what I mean is I'm going to distribute those fractions throughout. Okay. All right, so we do that. We have a 5,000. So I haven't forgotten about the 5,000. So the 5,000 will kind of apply at the very end of the analysis. Okay. All right. So first we have this 1/5 term, and so we have a 2/5 d1y minus 2/5 d2y. Okay. Plus 1/5 theta 1 plus 1/5 theta 2. Okay. Okay. Then we have the next term, which is everything multiplied by 1/4. And so this is going to be a minus 3/4 d1y plus 3/4. Negative is going to cancel negative. d2y. Okay. And we have a minus 1/2. Bless you. Minus 1/2 theta 1. Then we have a minus 1/2 or minus 1/4 theta 2. Okay. Then coming down here, we have a 1/3 theta 1 plus a 1/2 d1y. Okay.
Did it to be plus 1/4?
Mm,
Oh, sorry, I had minus on.
yeah. So this minus kind of distributes through here. Yeah. Although in my notes, I do have a plus there.
Yeah, on the top equation, the 2 theta 1 plus 3 theta 2. For some reason, I had 2 theta 1 minus 2 theta 2 before. I don't know.
Yeah, let me double check that real quick. Because in my notes, I do have this term being a positive here, but negative there. Yeah, so this, I mean, so this term should be 2 theta 1 plus theta 2.
Yeah, I think it's my mistake. I think
Yeah.
it's.
Yeah. So it's supposed to be minus. Yeah, thanks for catching that though. Yeah. With these problems, you can never be too careful because there's so many minuses and fractions and stuff. You want to be kind of very careful with that. And I remember this actually from last year. So I meant to correct this typo in my notes, but I didn't do it. So from here on out, we're flying by the seat of our pants because it's not in my not in my notes. Okay. And so of course the next step here, so we have a bunch of common terms here. So let's go ahead and combine the common terms. Okay. All right. So usually the way that I like to do this is that I kind of combine one set of terms at a time. And so let's combine all the d1y terms first. Okay. So let's go ahead and circle all of them. So we have a 2/5 d1y. We have a minus 3/4 d1y. And we have a plus 1/2 here. Okay. Okay. So for d1y, that's going to be 2/5 minus 3/4 plus 1/2 d1y. Okay. So let's go ahead and cross those out. Okay. Next we have the d2y's, and so we have a minus 2/5. We have a plus 3/4. I think that should be it. So plus minus 2/5 plus 3/4 d2y. Okay. Cross those out. Okay, let's do theta 1s, and so we have a theta 1 here, positive 1/5, minus 1/2 here, and a plus 1/3, plus 1/5, minus 1/2, plus 1/3. Okay. And then we finally have the theta 2 terms, which is a positive 1/5 and a minus 1/4. Okay. Okay. All right. Of course, all these are fractions which don't have a very convenient common denominator. That's kind of how it always is for these guys. Okay. So let's go ahead and combine these fractions. And so in theory, most of these are the same except for the 1 theta 2. Okay. Okay. And so if we combine these together, we have 5,000. Okay. So the common denominator between 5, 4, and 2 is 20. Okay. Very nice, convenient number. So this is going to be a positive 3/20 d1y. Okay. Then for d2y, we have a minus 2/5 plus 3/4. The common denominator for that is also 20. And so we have a plus 7/20 d2y. Okay. For theta 1, we have everything almost canceling out. So we have a positive 1/5 plus 1/3 minus 1/2. And so the common denominator for that is 30. And so we have a plus 1/30 theta 1. Okay. And then we have a 1/5 minus 1/4. And so the common denominator for that is again 20. And so that should be 1/20 because 1/5 is minus 1/20. Excuse me. So it's going to be 4/20 minus 5/20. So minus 1/20 theta 2. Okay. Okay. So last step here, let's go ahead and multiply the 5,000. So the 5,000 can finally have its chance to shine. Okay. So we multiply everything by 5,000, and what we get is 750 d1y plus 1750 d2y, okay, plus 500 over 3, theta 1. And then we have a minus 120, or minus 5,000 divided by 20. That should be 250. Minus 250. Okay, let me box this for now. Okay. That's basically our answer, but we have to kind of sort it out into the different components. Okay? Because what we've evaluated here is just the left-hand side of that expression, right? So this right here is the work done by the distributed loading. Okay. And then by our work equivalence statement, what we're saying is this is equal to the quantity of F1y, D1y plus M1 theta 1 plus F2y, D2y plus M2 theta 2. Okay. All right, and so from here it's just matching terms. And so we're going to see which term is the D1y, and so that's going to be our F1y. Okay. And so we circle this guy. Okay. Because that's the only term on both sides of the equations that are multiplied by D1y. And so this tells us that F1y is equal to 750. And the units for this is newtons. Okay. We can see here that the F2y is the only term that's multiplied by D2y. And so we have F2y is equal to 1750 newtons. Okay. The M1 is the only term multiplied by theta 1. So we have M1 is equal to 500 over 3 Newton meters. Okay. And finally, M2 is the only term that's multiplied by theta 2. And so this tells us that M2 is equal to minus 250 Newton meters. Okay. And then this is our final answer. All right. So let's check this answer to make sure that it makes sense, right? And so if we go back to kind of the original problem statement, we know that this is a load that kind of ramps up as it goes to the right, right? And so just visually, what we can see here is that there should be more load that's placed on node 2, right? So we should have more load on the right-hand side. And so if we look at our values for F1y and F2y, okay, we see that that's reflected in these numbers, right? And so F2y is over twice as much as F1y, right? And that's because the load is biased towards that right-hand side. Okay. So that makes total sense. And then the moments are kind of what they are as well. Okay. Right. So now that we have this answer here, we have our nodal modes. If this were kind of a more standard problem, we can actually use these to start solving the direct stiffness problem. Okay. And so when you have a direct stiffness problem that has distributed loads, you kind of have to do two problems at once. And so you have to convert the distributed loading to nodal loading, which is kind of a whole problem in itself. And then you have to take those loads and then apply that to the direct stiffness problem. And then you have to go through the whole shebang with that. So the element stiffness matrix and the assembly, boundary conditions, solving, and all that good stuff. Okay. It's like my friends always say. So my friends and I, we play a lot of massively multiplayer online RPGs where you can kind of create your own character. I have friends that will spend like literally hours in character creation, just changing their character. So they'll play the game for 12 hours and I'm like, oh, how's the game going? They're like, oh, we haven't started playing it for some character creations. And so they'll make their character and like, all right, now we can start the game. So now that we've done this, now that we've completed this nodal mode, it's like, all right, now we can start the problem. All right, any questions on this?
Sorry, could you pull up?
Yeah.
On the equation, a little bit more, where we had the interval from 0 to 1.
Yep.
Yeah, so. Okay, I think I had, a negative instead of a plus between the x to the fourth and then. Yeah, that's why I think the,
Gotcha. Yeah, it should be a plus.
or sorry,
Yeah.
down. Maybe, sorry, a little bit.
Mhm.
A little bit more.
Any other questions on this? Okay. All right, and so with that, we're going to close the chapter on direct stiffness methods. Okay, so that's all the theoretical information we're going to learn in this class. And so this is kind of the cutoff point for the midterm exam. So everything that we cover from this point, not going to be on the midterm, but it will be relevant for Kansas and everything. Okay. So we're once again kind of, we're going to shift gears pretty significantly and kind of go back to this stuff. Okay. Okay. And so, like I mentioned kind of at the beginning of class today, we've already kind of covered, everything that you need to know, at least in terms of general ANSYS. And so, what you guys are equipped with right now is good enough to run ANSYS in kind of its basic state and for most situations that you're going to be interested in engineering. Okay. From here on out, we're going to be covering more stuff within ANSYS, but this stuff is kind of more niche isn't the right word for it, but it's more specialized. And so, the stuff we're going to cover here is not applied to everything. Okay? But it's still important because there are some situations where these are kind of the only thing that you can do. Okay. And so the first kind of, I'd say more advanced feature we're going to cover in ANSYS is this idea of unsteady transient simulations. So this one's actually a fun one, and in fact, if you're going to run an FEA simulation on an unsteady situation, which a lot of you are kind of already doing, and so I've already talked with a lot of you who are applying FEA towards your senior design projects. You have situations that are transient, and so it's not a static situation. You have dynamic loads, you have dynamic forces and things like that, right? You can try to approximate these in a static situation, which is that's kind of the conversation I've had with a lot of you who have presented this to me. But if you want to do like a true dynamic simulation, you have to do it within a different framework. Okay. Okay. So kind of the definition of a transient simulation is basically any kind of time-dependent phenomena. So anything that has forces or has boundary conditions or even geometries that change with time. Okay. For the most part, it's going to be boundary conditions. Although there are some cases where the geometry can change with time as well. Okay, so anytime you have something that changes with time, you have to run it under a transient situation. Okay. Okay. And so the biggest difference that this makes is that we're no longer in a static situation, so we have to kind of get away from static structural. And so what you'll see in the activity next week is that we're going to be using a whole new analysis framework called dynamics. Okay. And what we'll learn, throughout the lecture today and the lecture on Tuesday is that dynamics has almost a completely different set of rules in terms of how to run the simulations. Okay? And so I will say that what we're going to cover in this class is kind of just a very, very quick introduction, almost like a flash introduction to all these concepts. And so if you kind of want a true kind of introduction to this, there's kind of other classes that you can take. Actually, the one that I do recommend is EGGM 403, which is numerical methods. And so, actually a lot of numerical methods concepts kind of apply here. We'll learn enough here just to kind of get you started to get you to run kind of a very basic dynamic simulation. But there's a lot of nuance and a lot of kind of extra considerations that you have to make in dynamics that you don't have to with statics. And so just kind of making you aware of that. Okay. Okay. And so kind of where we're going to start here is, because dynamics kind of uses a whole different set of rules, we kind of have to build up a kind of a different set of intuition. Okay. And so we're going to start with kind of a very basic model. And so just a very basic kind of lumped mass model. We'll talk about the characteristics of that model. We'll talk about kind of its expected results, and we'll talk about how that can be applied to ANSYS. Okay. So let's start with that. Okay. So let's look at a fairly simple lumped mass model that you've probably seen at least in some form in one of your other courses. Okay. And so the idea with the lumped mass model is that you have a mass of some kind. It's attached to a spring. Okay. And so the spring is going to provide some kind of restoring force, as we've talked about before. But we're going to talk about its time-dependent behavior rather than static behavior. Okay. Okay, so the one I'm going to use kind of looks something like this. And so we have a fixed wall on the left-hand side. Okay. In the middle here, we're going to have a spring. Okay, so the spring is going to have its own spring constant, K. We're going to have something here called a dash pot. And so that's going to provide some damping to the system. So those two things are going to be in parallel. And then attached to this all, we have our mass. Okay. Okay. And just to give it a little personality, we'll give it some wheels. Okay. Okay. And what we're interested in this model is tracking the motion or tracking the x position of this mass as a function of time. And so we'll call that function x of t. Okay. And again, we're going to have time-dependent behavior because what's going to happen is that this mass is going to, or what we say is going to oscillate. So it's going to move back and forth. Okay. Because what you can do, you can apply a force to this mass, or you can just say that we're going to give it an initial displacement. Okay. Give it a different color just to make it stand out. Okay. Right, and so if you apply force to the mass and then you let go, then this mass is just going to kind of just oscillate back and forth. Okay. Okay. Actually, let me label all the parameters here because they're going to be important. Okay. Okay, so first we have K. So K is the spring constant of the system. C is the damping coefficient. And M is the mass. So in a bit, we're going to talk about kind of the effects of each of these parameters on the behavior of the system, but I thought I'd define them first just to, just to give them okay. And so the behavior of the system, it can be described by the following differential equation. So it's a second order differential equation. So we have m d squared x dt squared. So if you notice that, that's the mass times the acceleration times c times dx dt plus k times x is equal to f. Okay. And so we're going to account for a case where maybe we're constantly applying a force f to the length. Okay. And that f could also vary with time. So we're going to say this is going to be f as a function of t. Okay. All right. So for our case right here, we're going to make the assumption that our damping is relatively small, and so we're going to be in what's called an underdamped regime. And so underdamped solutions kind of look like we call kind of a decaying oscillation. Okay. And so our x of t, the exact numbers for this x of t is going to depend, of course, on the numbers of the parameters, but it has the following form. So it's going to be a e to the minus dt, okay, times sine of omega t plus v. Okay. All right. So the exact values of those variables is not really important. In this case, it's going to be just the functional form, right? Because this function here is made up of two contributions. So we have a decaying exponential and we have a sinusoid. All right. So if we were to plot this, okay, so our horizontal axis here is time, and our vertical axis here is our displacement, x of t. Okay, it would look something like this. And so we'd start out with oscillations with very large magnitude. Okay, but then as time goes on, the magnitude of those oscillations starts to go down. Okay? Until eventually all of the oscillations will be damped out by the system and it returns to its quiescent state. Okay? All right. So why am I bringing this up, right? So why am I bringing up this idea of this lump mass system in an FEA course? Well, the lump mass system, as simple as it is, this is kind of a very elementary description of vibration in a physical system. Okay. And if there's one thing we know about physical systems is that they like to vibrate when you expose them to kind of sudden, unsteady loads. Okay. And so a simple kind of understanding of the lump mass spring, actually gives you a lot of really good intuition for how dynamic systems behave. Okay. And in fact, before the age of kind of high-powered computers of what we have today, engineers kind of use this concept of a mass spring system to kind of do vibration design of a lot of very big, complicated structures. And so I'm bringing this up because when you start to run dynamic simulations, you're going to observe vibrations that look like this, right? And so having a good kind of intuition, kind of a good kind of foundation, and kind of why those vibrations are happening, will give you kind of a lot of help in kind of interpreting your simulation. Okay? And so kind of key to this whole thing is kind of interpreting the three main parameters that go into a lump mass system. And so we named those three parameters above, but let's talk a bit more in terms of what they physically represent for a more complicated structure, and also what effect that those parameters have on the dynamic solution. Okay. Okay. So let's talk about the mass first. Okay. This one's perhaps the easiest to understand, the easiest to measure, right? The mass of a physical system is just its mass, right? It's a representation of how much mass is a representation of mass. You guys understand what mass is. It tells you basically how much inertia that system has. Okay? The more mass a system has, and if you recall from your physics courses, inertia is the ability for an object to resist changes in motion. So the more massive an object is, the harder it's going to be to change its motion, to change its momentum. Okay? And so the end result here is that as the mass of the system increases, it reduces the frequency of vibration. You have this kind of inverse relationship between mass and the frequency of vibration. Okay. Okay. So the next parameter that we'll look at is the spring constant. Okay. And so a spring constant, of course, is only strictly relevant for springs, right? But what we've seen, in our truss equations is that a lot of structures you can form kind of what's known as kind of an equivalent spring constant, right? It may not be, like for a truss bar, right? It's not coiled like a spring, but based on the combination of its length, its Young's modulus, and its cross-sectional area, you can get kind of an effective spring constant or an effective kind of stiffness constant for that structure. Okay. And so the spring constant, when you use it to kind of model dynamic systems, we don't really mean a spring constant in the literal sense. The spring constant is kind of more of an abstract idea in terms of, representing the overall stiffness of the structure. Okay. And so the overall stiffness of a structure can be affected by a number of its internal parameters, right? And so let's think about our truss bars, right? And so the parameters that go into the truss bar are things about its material, right? Its Young's modulus, for instance, and also its geometry, and so its length and its cross-sectional area. And so the overall stiffness of a structure is a function of its material and geometric properties. Right? So some examples, like the Young's modulus is a very key component that goes into its effective spring constant, right? So the higher your Young's modulus is, the higher your stiffness is, the higher your spring constant is going to be. Okay. And for the geometry, usually the length has an inverse relationship, and kind of the cross-sectional area or the width of your structure has a direct relationship. Okay. And so in terms of the effect on the dynamic result, generally the higher your stiffness gets, the higher your frequency of oscillation is going to be. So it kind of has the opposite effect as the mass. Okay. And so physically that makes sense, right? And so the stiffer your spring is, right, the more force that's going to exert to kind of bring the mass back to its equilibrium position, right? And so the more force that exerts, it's going to increase, the speed at which it rotates. It's almost going to be kind of like a rubber band effect. When you pull it out, right, and then the high spring force is going to bring it back, and then before it gets too far, it's going to bring it back up, and so on and so forth. Okay. So the stiffer your system is, the higher its frequency of vibrations. Okay. All right. And so the last factor here is the damping. The damping is kind of the most difficult um, feature to kind of measure, right? And so for the first two so far, we can get a pretty good sense of what the mass, I mean, the mass you should be able to measure exactly. And then for the spring constant, even though we may not have a spring, just based on its material properties, based on its geometric properties, we'd be able to get a good idea of what the spring constant is. Okay? The damping is a function of so many other factors that it's much more difficult to measure. But ultimately, its effect on the system is that it affects, how quickly oscillations can get damped down. And so some factors that can go into the damping are things like wind resistance, things like friction. Those are probably the two most common entries in that go into damping. But you also have some internal damping as well. And so you have kind of we call it kind of more like kind of structural damping or internal friction that can cause damping as well. And so as you can imagine, these things are much more not as inherent to the physical system itself, but kind of more inherent to kind of the stuff that's happening around the system. So it's a little bit different. It's a little difficult to measure. And in a lot of practical situations, you kind of measure this just by data fitting and by just observations. Okay. But you have to acknowledge that the damping exists, because without the damping, you just have kind of endless oscillation, which is just not physical at all. Okay. Okay. And so, practical situations, ones where you have kind of more realistic boundary conditions, realistic geometries, it may seem kind of hard to kind of fit exact values to these parameters here, with the exception of mass. And so I don't want you to think about that in terms of that. Okay. What I want you to more think about is, as we do the activity and as we run our simulation, right? I want you to kind of observe kind of the results that occur, the vibrations that occur, and think about how the stiffness of the system, how the damping in the system, how the mass of the system, how all of those things contribute to kind of what you're observing in the simulation results. Okay? Because if you were to make a change in one of those properties, say you use a material that has a higher mass, then you're going to see a change in the results accordingly. Okay. All right. Any questions on this? Okay. All right. And so with that in mind, let's kind of keep that in mind as we kind of run our dynamic simulations and as we kind of observe our results. Okay. Okay. So the next section that I want to talk about is the numerical solution to dynamics problems. Okay. And so the way that we numerically solve dynamics problems is quite different than what we've done before, right? So we've kind of just finished talking about direct stiffness, and we talked about how in direct stiffness, to solve an FEA problem involves kind of the construction of this kind of very large matrix system of equations. Okay, dynamic problems work a little bit differently because now instead of space being our independent variable, time is now our independent variable, right? And so time actually behaves quite differently than space. Okay. Static. And so by space, what I mean are kind of the space variables like X, Y, Z if you're going in 3 dimensions. Okay. Okay. And so the way static problems are typically solved is that, what I kind of describe it is that your solution at all points in space are solved simultaneously, right? And so they're solved all at the same time. Okay. And so what I mean by that is something like this, right? And so let's say that we have our direct stiffness system, we have a 2-dimensional truss, right? Maybe we have 4 nodes that we're solving for, right? And so we have our matrix here. Then we have our vector here, so maybe d1y or d1x, d1y, d2x, d2y, etc. Right? And this is equal to some forcing vector. Okay. when we solve this system, right, solving the system basically involves solving for the values of all the d variables, all at once. Then when we finish solving it, our results are all displayed at the same time too. So we can observe every point in spatial, in space at the same time. And so in other words, our result from this is basically a snapshot, a static image. And the reason for this is that, when you're talking about space, right, things, things kind of propagate through space very quickly. So when you make a change on one end of a structure, right, and you're talking about kind of a static situation, the other side of the structure kind of feels it kind of immediately. Right? And so there's kind of no sense of delay in terms of space. Okay? And so all points in space feel every change at the same time. I'm making it sound more cooler than it actually is, but if you think about kind of a table or any kind of static structure, right? And you make a change in one side, the other side kind of feels it immediately, just because it's a function of space. Okay. Time doesn't work like this, right? Time is what we call kind of a causal kind of variable. Okay. And so in order to solve for the solution at one point in time, we have to know exactly how the solution looked like at the previous point in time. Okay. And we can't kind of break that order. So we can't solve for something 3 steps in the future while we're still solving our current place. Okay. And so, you have to kind of solve things in time sequentially. Okay? And so due to this fact, the fact that, you have to solve for the time domain kind of sequentially, it presents kind of a new set of challenges to in terms of, how you actually find the numerical solution. Okay. Because you can no longer, solve a matrix set of equations, right? And so you can no longer, solve a system like this. And so maybe you have T1, T2, T3, T4, right? So this doesn't exist. Okay? You can't solve for the solution at all points in time, simultaneously using a matrix system. Okay. And so in fact, the method that we use for solving time domain problems numerically is different. And if you want to learn more, the kind of typical name that we use for these types of algorithms or these types of approaches are called time marching algorithms. So time marching is kind of a whole class in itself. And so, we're definitely not going to get into the details of time marching. We're just going to kind of deal with kind of the essential things that you need to know to work with it practically. But just know that it is a very, very large field, still very much a very active field of research as well. Okay. Okay, but the thing that I do want to highlight is that, because we're using basically different methods to solve the time domain, and because we kind of have this restriction of having to solve things kind of one at a time, one state at a time, what that means is that, our transient FEA solutions, our unsteady FEA solutions, are going to be a lot more expensive than our static cases. Okay? Okay? And if you look at the results of a dynamic simulation, it's going to make a lot of sense too, right? Because the nature of our results are going to change as well, right? Because no longer are our results going to be just a static image. Now we're going to have multiple static images that kind of each one kind of depicting the state of the system at a different time. And so when you kind of play it all at once, it's actually going to look like a video or movie. Okay? So one way that you can think about it is that an unsteady simulation or a transient simulation is going to be the simulation of lots of static frames, just kind of all linked from one to the next. Okay. And then for your results, you're just basically going to kind of layer those frames kind of back to back to back to each other, and you're going to produce a movie out of it. Okay. So that's part of the reason why, for an introductory FEA course like this, transient simulations isn't always covered, partially just because the theory behind it is very different. And also just running the simulations is very expensive as well. But I almost always do it every year just because I think it's important because I know a lot of you guys are working on unsteady problems. And so I at least want you guys to be equipped to at least set something up so that you can actually look at things in a dynamic way. Okay. All right. Any questions on this? Yeah.
The more expensive like element wise or also like complexity step wise?
It's much more computer intensive. And so it's basically like, you can think of it as eventually we're gonna get to a point next week where we're gonna say for a time marching simulation, you're solving basically 1,000 static simulations back to back to back. And so, you can think of it almost like having 1,000 times more expensive because you're solving the same thing 1,000 times. Just each time the conditions are going to change slightly. So it's mostly in computational time. Yeah, less memory, more CPU. Yeah. No, this is for dynamic and elastic simulation as well. Yeah. So we're gonna have rigid body motion. So the activity that we're gonna do next week is we're basically simulating a car crash. And so it's going to start as rigid body motion, and then it's going to basically crumple itself. Yeah. Mm-hmm. Any other questions on this? Okay, all right. So that's all we got time for this week. And so when we come back on Tuesday, we'll finish up this lecture, and then next Thursday we'll do our next activity. Remember, the next activity we're going to start it next Thursday, but it's not going to be due till after Thanksgiving, just so you guys can focus on the Tuesday. Okay. All right, so thank you guys for coming this week. Hope you guys enjoy your weekend, and I will see you guys next week. It's gonna be the Thursday before Thanksgiving, so it'll be Thursday, November 16th, 2 weeks from today. Yep.
So, I don't know, I know you said it's not steady state, but, like, does the fluid mechanics involve, counted as?
Oh, yeah.
Example of this?
Oh, yeah, yeah. So for most fluid mechanics simulations, those are gonna be dynamic. And so if you take a CFD course, and so I know Dr. Myrola is offering one next semester. And so certainly he's gonna be talking about some of this, but there are static fluid situations, but we're not interested. So if you're gonna do fluid mechanics, you have to know about dynamics.
Okay. So, okay, because like, it's not only like just maybe, the way I'm thinking of is that like, oh, we have, let's say, if I wanna make a simulation of a pipe, I wanna put like something similar to like Bernoulli and apply it.
Yeah.
But like, I mean, in fluid mechanics, we assume this steady state, like, all these assumptions, so.
Right.
Are we gonna still do this, are we gonna apply these assumptions in the simulation or?
Yeah, you can do that. And so I mean, static, you can still do a static fluid simulation. It's just that a lot of the practical cases, a lot of the interesting cases are dynamic.
Okay, so there's like, it's not, it will not be a study motion anymore.
Yes, because a lot of times when you have fluid motion, you have turbulence too.
Yeah.
And so with turbulence is just naturally unsteady. So it's impossible to do a steady turbulence simulation.
So it's only, so usually you guys, or like, sorry, I don't know what to say. In like, let's say in the theoretical part, for example, in fluid mechanics, most of our examples are, most of it's like steady state. I forgot about, I forgot the other assumptions.
Yeah,
I forgot about.
those are all pretty ideal cases.
So yeah, it's only applied for the like fluid mechanics, theoretical part, because it's make it easier to understand the
Exactly.
concept.
Exactly.
But when it comes to simulation, since the computers can't do that, you just
Exactly.
we just like put it and make the solution on it.
Exactly. Yeah. Yeah. Yes, so it's gonna be the same day as this one, it's on November 16th, so 2 weeks. Yeah, we'll talk more about it. Yes, I did. Yeah, so something, introduction, something motivational, and then,
Whatever you want to share.
Okay.
Or whatever you like to share.
okay, all right. Maybe I'll talk to Dr. Bell about that. Like, I don't know exactly what's there.
Okay.
I think we should talk about maybe something that's part of the show.
Okay.
But what's the approximate length of the?
I think it's like anywhere from like semi-short, like 15 minutes. I don't think it's gonna be like that. Okay. Like 5 to 15 minutes.
Okay. Just talk, right? No, it's my thing.
Yeah, if you want to prepare anything, you can. If not, you can just talk. It's like just up to you. I think some of the other things, guys, just have like the, it's like, you know,
Okay. Yeah. Okay. I think right now I'm going to be talking with, just kind of sharing my experience and then we'll go.
okay, that sounds good to me. All right. Yeah.
See you Saturday.
Yeah.